Hello viewers, so welcome back to the course on matrix computation and its applications. So, we will continue with some other examples of linearly dependence and independence, and we are also going to discuss some important facts about that one. So, let us start with that. So, this is lecture number 10. Now, in the previous lecture we have started with the definition of linearly dependence and independence. So, in this case I am taking one example that belongs to the C 0 infinity. So, it is a space vector space of all continuous function defined on the interval zero infinity. So, this is vector space, another type of vector space in which all the continuous functions falls which are defined on the interval 0 to infinity. So, for example, if I want to check the elements of this vector space, then you can say that exponential belongs to this, or maybe polynomial x square plus 2x plus 1 belongs to this, or maybe I can take log function because x is not 0. So, no problem. So, this belongs to this one, or sin x, tan x. So, all these type of functions they belongs to this category. Okay, so, this type of function, and it contain infinite number of functions. It is just I am giving few examples. So, it can be a e minus x, it can be a e 2 x. So, if you see from here, then it contains infinite number of elements belongs to this space. So, it is a vector space. Now, in this case, suppose I take a set of the elements, and element I am choosing just taking x, and suppose I am taking sin x, and suppose I am taking cos x. So, just 3 elements from this one, and I want to check linearly independence or dependence of these vectors. So, I am talking about this vector. These are the 3 vectors belong to this one. Now, in this case also, so let us take the linear combination. So, linear combination is I am taking a x plus b sin x plus c cos x equal to 0. Okay, so, in this case my x is coming from this interval, and a, b, c are the scalars. So, that we are going to find out just to check whether they are linearly independent or dependent. So, I just taken the linear combination and putting it to 0. So, this 0 is a 0 function. So, it is basically, if we want to check the C 0 infinity is vector space or not, then we have to take the 0 function as a additive identity. So, this is the additive identity 0 function. So, now from here I get this. Now, the question comes that how we can find out the value of a, b, c, because this is just the one equation. So, in this case we just take the help of some other concept of the function. Now, we know that this function belongs to the C 0 infinity, but from here also I know that x I can is a polynomial, and even I can take the derivative of this also. Sin x also I can take the derivative, cos x also I can take the derivative. So, this function are differentiable. So, I can just write 1. So, I can just differentiate equation 1 with respect to x. So, I just differentiate. So, from here I can get it is a plus b cos x minus c sin x equal to 0. So, I get the second equation, but I need to take the help of one more equation, so that I will get 3 by 3 system. So, again, so after this one again differentiate 2 with respect to x. So, this will be, I am taking just a x, and so x, the derivative x is 1. So, here now it became just constant. So, it is 0 plus then minus b sin x, because the derivative cos x is minus sin x, and this will be minus c cos x equal to 0. So, this is my third equation, and the function which are differentiable, that is also member of this one, because a function is a differentiable, definitely it will be a continuous function. So, from here I get this value. Now, from here I will just write this into the form of a matrix. So, it will be A, B and C, and then it is, I can write from here x, it is sin x, it is cos x 1, cos x minus sin x 0 minus sin x minus cos x, and that is equal to 0, 0, 0. So, from here I get a matrix, a homogeneous system A x equal to 0. Now, I have to find out the determinant of this one. So, let us take the determinant. So, I just want to find the determinant of A. So, let us find out. So, it is starting from the first column. So, x and then minus cos square x and then minus sin square x minus 1. So, this is minus 1. So, it will be minus sin x cos x and then plus sin x cos x. So, that is my determinant, and this is cancelled. So, from here I can get this value minus x, and it will be sin square x plus cos square x, and that is 1. So, from here I will get the value minus x. Now, the determinant of this is minus x. Now, from here if you see from that x is coming from interval from 0 to infinity, and 0 is not the member of this interval because it is open interval. So, from here we can say that the determinant of A is not 0 in this case, because 0 does not belongs to this one, it is open interval. So, from here you can check. So, from here since my determinant is not equal to 0, so I am going to have x is equal to A inverse 0, and that will be 0. So, from here I can have my A, B, C both, all the 3 are 0, and from here you can say that the vectors, so the vectors x, sin x and cos x are linearly independent. Okay, so, from here this type of things we have to do when we deal with the space of continuous function or differentiable function like that. So, this is the way we can do. Now, so after doing this example, so let us take one more example based on this, because sometime I just take one more example. So, let us consider complex vector space. So, complex vector space means the vector space we define on the complex number C. So, instead of the field of real numbers, we are taking the field as set of complex numbers. So, in this case we are taking this one. Now, so let's I choose the set S, that is I just take 1 and I. Now, I want to check whether they are linearly independent or dependent. Linearly independent or linearly dependent. So, I will take the linear combination. So, in this case now the field F is set of complex number. So, it is set of complex numbers. So, in this case my scalars are complex numbers. Okay. So, let us take scalars. So, I just take the scalar A plus I B, this is a scalar plus 1 C plus I D I equal to 0. So, I just take the linear combination. So, this is my linear combination, and from here I can just collect the real and imaginary part. So, from here I can say that A is real, and if I take I here, so it will be minus D. So, it will be A minus D plus I B plus C, that is going to be 0, and this is a 0 complex number. So, comparing the real and imaginary part, so from here we can write that we get A minus D equal to 0 and B plus C is equal to 0. So, this is we got A minus D equal to 0 and B plus C equal to 0. Then from here A is equal to D and B is equal to minus C. So, I got from here. Now, from here I can write this as A is D. So, I can write D plus I B is minus C plus C plus I D I. So, this one I can write as, so D minus I C and C plus I D I equal to 0. So, this one I get from here. This part. Now, so from here I can have this combination, and one more also, if I take the elements 1 and I. So, I know that I can be written as I into 1. So, this one I can write that one vector can be written as a linear, the scalar multiple of another vector. So, another vector is 1 and this is my scalar. Okay. So, from here you can also check that 1 and I are linearly dependent, because even they no need to do all this one, we can also verify from here that one vector can be written as a scalar multiple of the other. So, in this case I will say that these two vectors are LD, 1 and I, they are linearly dependent. Now, so the same question, so it is a question number 1, I can write question number 2. what will happen if we take the vector space V over the real line. It means I have the set 1 and I want to check whether it is LD or LI. So, this one I want to check, but now I am taking this vector space. So, vector space of real numbers. So, scalar is coming from here. Now, we know that since we know that I cannot be written as some alpha into 1, where alpha belongs to real number. It is not possible unless until alpha is I, but we cannot choose alpha as I because we are taking the field as a real number only. So, in this case I can say that the set 1 and I are linearly independent. So, the same set of vectors, but we are taking the different vector space. Here it is a scalar field is equal to real number, then they become Li, and if you take the vector space over the complex number, then they are LD. So, this is one of the examples of having the same set of vectors, but coming from the different vector spaces. So, this one now there are some few facts we want to discuss. That in a vector space V, if I take that V is a linear combination of V1, V2 and Vn, that is I can write V as a alpha 1 V1 plus alpha 2 V2, because this vector V is a linear combination of the vectors. It means that V belongs to the span of this. So, it belongs to the span of these vectors. Then if I take the set of vectors, adding that vector V, then they are always LD, linearly dependent. So, this is just the fact here, and the proof is very simple. It can be a theorem also, but just we are discussing in the same of facts. Now, given that V belongs is a combination of alpha 1 V2 alpha 2 alpha n Vn. It means V can be written a linear combination of these vectors. Now, I want to check what this set. So, it is given. Now, I just take the linear combination of V A1 V1 plus A2 V1 A3 V2 A n plus 1 Vn equal to 0. So, let us take, now let us take linear combination. So, this is the set of vectors and I take just linear combination. Now, from here that is given to me, and I want to find out what is going to happen for the scalars, that it is whether it is going to be a Li or LD. Now, from here I can write this as A1 V, I just take on the other side. So, maybe I can just write this as I can write A2 V1 plus A3 V2 An plus Vn, I can write as a minus A1 V. This one I can write. Okay. Now, from 1 it is given that V is a linear combination of V1, V2 up to Vn. Okay. So, from here I can write this minus V1 minus, I can write minus V plus alpha 1 V1 alpha 2 V2 alpha n Vn equal to 0 from 1, because just I am taking the minus 1, and now it became the linear combination of this one of V, V1, V2 up to Vn, and the coefficient is coming minus 1 always. Okay. So, from here I just can say that the set of vector V, V1, V2, Vn are linearly dependent. So, this is just become the linear dependent. So, from here I just choose my A1, I just can divide by A1, or I can choose my A1 is equal to minus A1 is equal to 1, and then it becomes the same thing. So, from here we get that this is linearly dependent. So, maybe I can take this rules concept directly from here also. Just I will apply this, then take the minus V and then become the linear combination, and then we get the linear dependent. Okay. So, from here we can say that they are linearly dependent. Now, the another fact is that let the set, so the first one, if the set is Li, so Li means linearly independent, then any subset of it is also linearly independent, and if a set is LD linearly dependent, then any superset of it is LD. So, let us do this one, the first one. So, suppose I have a set S is linearly independent. So, suppose I just take the S as V1, V2 up to Vn. Okay. So, and suppose this is Li. Let S is this one and S is Li. So, from here if I take A V1, A1 V1, A2 V2, An Vn, that is going to be 0. Okay. So, that is there, and all my A1, A2, An all are 0. So, that is the meaning of linearly independent. Now, I take any subset. So, let us choose any subset of the set S. So, let us take so say I choose S1 as just V3, V5 and maybe V11, just 3 members I choosing. Okay. Then I just want to check what is going to happen in this case. So, I can write from here A V3 plus B V5 plus C V11, and I put this equal to linear combination like this one. Now, this is coming from here. So, this is a subset of S. So, these elements are coming from here and S is itself a linearly independent. So, this one I can write, we can rewrite it can be rewritten we can rewrite one as, so I can write this one as 0 V1 plus 0 V2 plus A V3 plus 0 V 4 plus B V 5, similarly 0 V 10 plus C V 11, 0 V n, that is equal to 0. I am just adding 0 0 0 from here. Now, this became the linear combination of the vectors belonging to the S, and which is a linearly independent. So, from here, since V 1 V 2 up to V n set of these vectors are linearly independent. So, from here I can say that B is equal to C is equal to A, all are 0. So, from here I can say that S 1 set of vector is also linearly independent. So, these vectors are also linearly independent. So, if I take any subset, then it is coming linearly independent. So, this is okay. Now, we can take the next one, that if the set is LD, then the superset is also LD. So, the proof, so this is the second one. Now, let us take a set as, suppose I take V 1, V 2, V 3, and let me take this set S, and V 1, V 2, V 3 are linearly dependent. So, from here it means that suppose A 1 V 1 plus A 2 V 2 plus A 3 V 3 are 0. So, this is equal to 0, and A 1, A 2, A 3 belongs to the field F, and they are need not be 0. So, they are LD. Okay. It may be 0 or not, does not matter. Now, if we choose a, so if we choose a superset of S. So, superset means that a set which contain this S is a superset of this S. So, let us take it S 1. So, S 1 will contain the elements, some elements I can say as a U 1, U 2, some elements there, then V 1, V 2, V 3 are there, and U n something like this one. So, that is, so from here I can say that S is a subset of S 1. So, S 1 is a superset of this. Then I can find out from here that if I take the linear combination like alpha 1 U 1 plus alpha 2 U 2 plus some alpha I V 1, alpha I plus 1 V 2, alpha I plus 2 V 3, and some alpha n U n, that is going to be 0. Now, in this case I want to check what is going to happen for this set of vectors. Now, from here you can check from here that we can choose all alpha 1, alpha 2, alpha I minus 1, and then alpha I plus 3, alpha n equal to 0. We can choose, no problem. Okay, because linear combination this, so I can choose any alphas. So, suppose I choose this one, then I will only left with these 3 points. So, from here I can have 0 U 1 plus 0 U 2, alpha I V 1 plus alpha I plus 1 V 2 plus alpha I 2 V 3, 0 un equal to 0. Now, this is already known that these are LD. So, we know that this set V1, V2, V3 are LD. Since V1, V2 and V3 are linearly independent LD, so it means that this can be 0 or not be the 0. So, but other elements are 0. So, from here I can say that even the set U1, U2, V1, V2, V3 and Un, they are also linearly dependent, because in this case we have taken a sum set S belongs to this, which contain only 3 elements that are linearly dependent, and then we have taken one superset of this one, and then we show that this is also linearly dependent. So, it means that if I choose any set S that is linearly dependent and this is contained in any set S superset, then the whole superset, I just take it S1. So, S1 is also linearly dependent, but in this case I have some set S is Li linearly independent, because I have taken this set Li, and then I can choose any subset of like this one from this one. So, this is also Li, this is Li, this is also Li. So, they are linearly dependent. So, one is taking the superset and then finding in subset, and another is we are taking the small one and finding the superset of that. So, this is the way we can define these two facts. So, we will stop here now. So, today we have discussed few examples, a new type of examples about to check the linearly dependence or independence, and then we have discussed two facts about the superset or the subset of the linearly dependent or independent sets. So, in the next lecture we will continue with this one. So, thanks for watching. Thanks very much.